We're going to start out looking at the chain rule from simple perspectives, and then the next video we're going to introduce use substitutions, because that's the way I would prefer to use the chain rule, but we'll work our way up to it. First of all, we all remember, please excuse my dear Aunt Sally, in parentheses exponents, but really it should be grouping symbols, powers, and so on. So it really should be, gosh, Patty, my dog ate Sally, or something like that. The reason I bring this up so that we can interject the only humor in this entire video, but also because I want us to remember that if we have radical 7, we can write that as 7 to the 1/2 power. A radical is a power. All right, so here we go. Here's the chain rule. You use it when you could write your original function as the function of a function. So if we could write y as a function of x, but think of it as some function of another function, then we can use the chain rule. And what we do is, to find the derivative, we take the outer function with respect to the inner function, and then we multiply that by the inner function with respect to x. So let's suppose we see it this way. We'll use a little color coding. We're going to say y is equal to f of g of x. So what we're saying is the derivative would be take this and multiply it by that. Let's see how it works. All right, let's make sure that it's legit. Let's do this function. Let's take the derivative of this with the chain rule and then see that it gives you the same result as if we used the power rule. So if we did the power rule right away, y is equal to this cubed. So if we cubed both these factors inside here, we would end up with 8x to the 6th. Now taking the derivative of that function with respect to x, multiply in front by the 6 and reduce the exponent by 1, we should get 48x to the 5th. So let's see if using the chain rule would do the same thing. So what we're going to say is the outer function here is a cube and the inner function is 2x squared. So we're taking the function of a function, and the outer function would be to cube something. So the derivative would look like this. If you cube something, if you have something cubed and you take its derivative, you multiply in front by that exponent and reduce the exponent by 1. So we've taken care of the derivative of the outer function with respect to 2x squared. Now we need to multiply that by the inner function and its derivative. The derivative of 2x squared is 2 times 2, reduce it by 4x. So if we clean it up, 4x times 3x gives us the 12x times this guy raised to the 2nd, just to make sure it does agree with the derivative we get if we expanded and used the power rule. This guy would become this, and eventually, by golly, yes, the derivative using the chain rule is equivalent to the derivative we'd get if we expanded and used the power rule. If we look at this guy, what we have, the outer function could be considered that we're taking the 4th degree of something, and the inner function would be this bad boy right here. So the outer function, we take the derivative of it, so we multiply in front by 4, reduce the power by 1, leave that inner function the way it is, and then multiply it by the derivative of the inner function, so we end up with this being the derivative of that puppy right there with respect to x. This guy, if we're taking the radical of this, we can look at it as taking the radical, the outer function is the square root, I prefer to call it the radical of the inner function 3x minus 1. So we can write it this way, because remember, we want to use rational exponents or negative exponents to make life easier for us. So we're taking the radical of this inner function. Okay, take the derivative, multiply in front by the 1/2, reduce that by 1, leave this guy alone, and then multiply it by the derivative of the inner function. So this is what we get. We know that that negative exponent means let's put it down in the denominator as a radical, and we clean it up a little bit, and voila, that's what we get for the derivative. This guy's a little bit uglier, so we could mess with it a little. Let's first, again, say no, let's not leave any variable factors or parts down in the denominator. So let's rewrite this as the function f of x minus 1 raised to the -3rd power. So what we have then, if we look at the outer function as being something raised to the -3rd, then we're going to multiply in front by a -3, which obviously, oh, and there we go. Okay, so we're going to rewrite this like this. So we're going to multiply in front by -3, reduce the exponent by -4, leave the inner function alone like that, and then multiply by the derivative of the inner function. And so if we clean this up a little bit, you can see how we want to make sure we move this negative fourth power back down to the denominator. And we should get this result for our derivative. All right, but the chain rule really gets its name when we apply it to more difficult situations where we'd actually need to take the derivative of the function of a function of a function. So after watching this intro, you should watch the video on chain rule sophistication, because again, I would really prefer that we use the chain rule and see it by making use substitutions, which become very valuable to us the further we go into calculus. So one last shot, finding derivatives. Using the power rule, you know to use it when you just have a variable raised to a power. We can take the first derivative, we just multiply in front by the power and reduce the exponent by 1, and we're done. We use the chain rule when we can see our function as being the function of a function, when it's a little bit more complex. So we would rewrite our function as the function of a function, we start cranking away on this bad boy. So the derivative would be to multiply in front by the power, reduce the power by 1, leave this guy alone initially, but then multiply in the end by the derivative of this, which would be 6x minus 7. And then we would go ahead and clean that up. But that's an initial look at the chain rule. If this is easy for you and you're able to see it that way, that's fine. Otherwise, the next video, when we handle the even more sophisticated functions by using use substitutions, if you struggle at all with this, the use substitution approach should make these easier and hopefully make the other more challenging problems doable.